Okay, so welcome to part 3 of this openLCA lesson series for giving you some support for the EPD course project. So now we're going to focus on results interpretation in the context of presenting EPD results. So I'm going to break the video into two. So the first one's going to just focus on understanding results outputs from openLCA. Second one will be what results to present in your detailed LCA report for your EPD. This is more suggested recommendations, and we'll kind of go into PCR requirements and the potential for showing certain analysis. Okay, so let's turn over to openLCA. So I'm going to continue with the example from part 2, which was the steel production converter unalloyed process that we created with 5 modified eco-invent unit processes representing key activities along the supply chain of producing steel. So our functional unit was going to be on the steel production process, unalloyed steel, and we're going to, we already created a product system, so you can see it here, and I have it open. So now we're able to calculate results. So if you press calculate, you have the option for several types of results, and right now for this lesson I'm going to go through quick results and analysis. So I've already ran this, so I'm not going to run it again, and I have the results here. Okay, so now I'm gonna go through each tab to give you an idea of what's presented, and I've written some a supportive slide to sort of explain it as well, and relate it to some of the equations you're already accustomed to knowing in terms of the matrix algebra. So the first tab is just general information. It provides top 5 contributors to flows. So flows as in elementary flows, whether it be a stressor, an emission to nature, or an extraction from nature, like iron ore. And then the top contributors to the impact category results. So I ran Tracy 2.1. I recommend that you run that one as well for your EPD. And so you can basically select any of the impact categories and get an idea of the most important activity in the system. So this is just showing direct impacts of a specific activity in your system. And so it's not really that useful. It doesn't really tell you why the impacts are occurring, but it can quickly allow you to understand what's the biggest hotspot in your system. So for example, with global warming, CO2 equivalents, we see that the most important direct contributor is the pig iron production process. So that's definitely useful information, and it doesn't hurt to present some results that show, say, the top 5 contributors or top 10 contributors. That could be a good thing to show. So I'm going to, if I go back to my slide, I'll just show you what that looks like. So okay, I didn't actually bring up the general information tab here, so let's just go to the next one. So inventory results is basically showing you the cradle-to-gate requirements for your given functional unit, in this case a kilogram of unalloyed steel. So it's going to be showing you the total amount of inputs you need from nature and the total amount of outputs to nature, and along with the total requirements, so the total output of every single activity in the system, so products from the system, and that can easily be related to so here's sort of the tabs that I'm describing in this slide. So inventory results, it's simply this calculation, right, that we're well aware of to get the total output. The total product output is simply the Leontief inverse multiplied by the final demand, which is 1 kilogram of steel at that process, at our focus process. And then likewise, elementary flows, same calculation. You just add on the stressor matrix, which is here, to get the total outputs or total elementary flows, so from and to nature. So pretty self-explanatory. In terms of usefulness, it's very disaggregated information. So unless you really have a very specific question in mind, it might not be that useful for presenting results analysis in your report. So the next tab is impact analysis, and it has this little cutoff percentage, and that relates to a filter in terms of what end contributing processes are to be considered in, for each impact category. So it's a percentage in terms of total impact, and if a process contributes more than that cutoff, then it will be shown here. So we can like if we increase the cutoff, then basically you get less and less processes, and as you increase it, you get more. And this can be useful to show, the top end contributing processes, activities. So in terms of direct impact, and that can be useful to show in terms of getting an idea of hotspots. It's a little bit more information than, say, the top 5. And also what's very nice about it is that you can quickly understand what stressors are actually contributing directly to that impact. So this is basically telling you 100% should give you 100% breakdown in terms of what stressors are causing this impact of 0.76. So as you see, the inventory result for CO2 is here, the impact factor being used is here, and we understand that 100% of the impact that's contributing to global warming at this process of pig iron production is basically all due to CO2 emissions. But like if you look at hard coal mine operation, you'll expect some methane as well. So you can see the inventory result, so the elementary flow result or air emission of each molecule, and then you see the related impact factor and the amount it's contributing. So you can see that in this case, methane is actually contributing more, right? So this is quite nice, and what you can do is you can open all this up, and then for basically everything you're interested in showing for your analysis, and then you can basically select, hold shift and select the whole table, right click, copy, and you can open up an analysis workbook for your system, and you can copy everything into it exactly in the same frame that you set up in your tool, right? And so this can be quite useful for looking at specific contributions, and you can get into some pretty good detailed analysis in your write-up, which we'll get into later. So I won't go too much into presenting the results, but so this is a very good results output that you can use to quickly understand top contributing processes and the related stressors. But still, what's not so good about it is that you don't really understand necessarily why these activities are important. Of course, we pig iron production was a process we created, so we have a very good understanding of why it's there, in the supply chain. But for example, hard coal mining operation, or hard coal mine operation and hard coal preparation is an important process, but we don't know exactly why it's important, because we don't know where it's being used necessarily. Of course, as we have good understanding of our system, we'll have a better understanding, but you have to keep in mind that this is like total system impact. So some of this impact could be due to requirements at sinter production, but it could also be hard coal required at a completely different process in the value chain. So that's something to be aware of. So if we go back to the slides, I can just show you quickly. This is sort of a summary of what it represents, and we're well aware of how to calculate the total impact. D total impact equals the characterization matrix times the stressor matrix times the total output, or broken down further like this. Okay, good. So now let's go to the next tab. Okay, this now quick analysis. This is sort of where it stops. There's a couple other tabs, but I don't really recommend getting into them. Locations is more to do with where the impacts are occurring in your system, but since EcoInvent isn't very reliable in terms of having a good comprehensive understanding of where the regional impacts are occurring, it's not really that accurate. Like, it says a lot of the impact is happening in China and the US, and that's, that's not really accurate. But if you have a very comprehensive foreground system and you have it regionalized very well, then it's a little bit more reliable, and you can focus on like things that, processes that you're well aware of that are occurring in a specific region. And grouping is a way to basically group all the activities in your system, and I don't necessarily recommend it that much because it's kind of tedious. Like, you can create, say, a folder called transport required, like that, or any category you want, right? And you can essentially start moving things, but there's no search algorithm here to kind of pre-filter processes, so it's kind of tedious to figure out where what you want to include. It's just in alphabetical order, right? And so, but the idea is that you can select processes, right click, and then move it to your prescribed folder, and then that's going to give you a breakdown in terms of contributing activities based on your folder breakdown. So based on what I selected, it doesn't really contribute anything. These particular activities in the system don't contribute anything. So I don't really recommend using it at this point. And so that's basically what quick results will show you. So we can go on to the more detailed analysis. So let's start with the first tab. So this is the same, so I won't talk about it more. It's the same as what you find in the quick results. Same with inventory results. Impact analysis likewise is the same. Right now I have it on 0% cutoff, and so you can get a better idea of like how many more processes are being shown. So this is the top end contributing activities broken down, and so you can see that as you go further and further, now a lot of the activities are really contributing very little to the process or to the total impact of the system. But you can copy all that into Excel and do further analysis. If we go to process results, so what this is showing is basically you can select a process, an activity in your system, in your database, whether it be foreground or background. There's no differentiation, but right now we have it on, it's on the focus process, and you can see 100%. So what does that mean? That basically means that this is showing you for that particular activity what it's responsible for from direct and upstream impacts. So since this is the last activity in the system that's pulling on the demand for the rest of the system, it's responsible for all of the impact. And so it has that breakdown for flow contributions and also impact assessment results. Right now I have it on sinter production, which was a process we created earlier, and we can see that this is what it contributes to in terms of what it's responsible for. So it's direct and everything upstream. So this equation I actually haven't introduced you to in terms of how to calculate it, but it is possible to derive with matrix algebra. And so basically what you do is you calculate you calculate the total output, and you then so you calculate the total output, and then you diagonalize it, and then you recalculate it. So you're essentially acting as if your final demand is actually your total output. So as you're used to seeing SL times Y, which is the final demand, now we're going SL times X, and X is the total system output. And when we diagonalize it, then we'll understand whatever every single activity is responsible for in terms of its direct contribution and everything upstream. And likewise, you can do the same thing to get, so that's for flows, elementary flows. I just put a little LC to stand for life cycle. And you can do the same thing for the impacts. You just add C. You just multiply by C, and then you have the same outcome. Yeah, I sort of skipped that part here, but that's okay. And then the relative part, you see it in terms of percentage contribution there, or percentage contribution here. That's just a matter of dividing by the total, dividing that matrix by the total, and that matrix will be found in Excel as well. So whether or not this is useful, I would say it could be, when you want to look at a specific process, to understand that what it's responsible for. But essentially that's what the contribution tree is also doing, and it's presented in a nicer way. But you have to be mindful that it's a little bit aggregated in terms of there being what looks to be like a preset cutoff. In other words, it's cutting off a number of contributing processes. So let me explain that a little bit more. So we understand 100% of the impact is due to the steel production at our plant gate, and then we see 75% is due to pig iron and everything upstream of pig iron. So this can also be seen when you learn about Taylor series expansion. We learned about 0th tier, 1st tier, 2nd tier. So this is like the 0th tier, 1st tier. Then this column is the 1st tier, and then this column is the 2nd tier. This column is the 3rd tier and 4th tier. 0th, 1st, 2nd, 3rd, 4th, 5th. So we're going upstream, and we can look at it in terms of tiers. Now, if I aggregate all of this, so we see 75%. And so what I meant by cutoff issue is that, you can see that this isn't necessarily adding up, right, to 75%. And that's just because there's a lot of contributing processes that just aren't contributing that much. So they get cut off from the system. But nevertheless, it's telling you the absolute contribution of that particular sub-supply chain. And so it's useful to pinpoint the reasons of why there's an impact occurring. So we can break that down even more, sinter production, and then we look at our key processes that we created. Iron ore beneficiation contributes 1.23%, but a certain percent of it is due to iron mine operation. So 0.43% of the total impact is due to iron mine operation. And so we can open this up, and in a similar way we can copy this like this screen into Excel, just by selecting the top row and then shift and then clicking, and then we can copy it in whatever detail we want into Excel to provide further analysis of key sort of value chain contribution. So they're using an algorithm for essentially structural path analysis, which is quite insightful as well. But just be mindful of the fact that there is a certain cutoff, so it's not necessarily exhaustive. Like I'll show you if I copy this first tier results, right click, copy, and I go to a workbook, and I then copy it. I can see that this is 100%, but if I add up what it's showing here, it's adding up to 96.1%. So it's not exactly adding up to 100%. So there's a certain cutoff that's being considered, but nevertheless, it's useful because it is telling you like the actual amount due to this supply chain. It's just not telling you necessarily everything. So if you wanted to show at this resolution, this first tier resolution, the contributions, you'd have to add other, and then just go, this would equal 1 minus the sum of what's being shown here, like this, like that. So we see that there's about 3.9% missing. All right, so if we go back to, and I didn't explain too much in this slide. I just said, yeah, it's sort of a nested contribution by value chains, and a structural path analysis algorithm was used. Likewise, there's grouping and locations. I won't open that. They actually do have an option for sunburst. It's a development. It's under development, but if you go to preferences, you might not see it right away, but if you go to preferences, you can go experimental features and select experimental visualizations, and then it'll allow you to see this. This might be a little bit useful, but it's not really easily extracting information, but it gives you that kind of quick understanding of like, okay, wow, this is a big impact. What is this? And then you can click on it. You see, okay, this is due to Coke, market for Coke, which is going into the pig iron production process. So we can immediately say, well, this is an important hotspot. We should discuss it. Of course, there's other ways of looking into it, right? We can go to the contribution tree, and we can go to the pig iron, and we go, okay, there's the Coke, and so right away we see 13% of it is occurring here. Okay, so I think that's about it. Yeah, there's also the Sankey diagram. As you can see, it can get very messy very quickly, depending on it all depends on like what is the cutoff. And so if I change my cutoff to something a little bit more manageable, it's not going to be so messy. Sorry, I don't have my other mouse, and I'm having a hard time zooming in, but like you can get an idea of what it looks like. So what a Sankey diagram should show is basically the width of the line is representative of how much impact or how much flow is occurring due to that particular value chain. So it can give you a little bit more insight into connectivity. All right, so now let's look at the outputs to Excel. So the simple analysis. Let's just look at the file first. So I just downloaded it, put it in my downloads. So immediately you can see like, wow, this analysis calculation is way bigger. It's like 312 megabytes, whereas the simple quick analysis is only 5 megabytes. So we can kind of ask like, why is there such a big difference there? So if we go to the quick analysis, we can see if I just right click here, we can see the sheets that are available. And so we have the inventory. That's the same as inventory analysis that I already showed you. So it's the cradle-to-gate. We have impacts. That's just the total impacts, process flow contributions, process impact contributions, and flow impact. So let's go through each one. Okay, so inventory analysis, again, it's just showing you the total cradle-to-gate or cradle-to-gate grave, in this case cradle-to-gate requirements in terms of flows and in terms of activities, so products. So it's not giving you any insight in terms of why we require this much, but it's just telling you the total amount. So maybe you have a specific question about a product or a flow, and you just want to understand the total system requirements. Like maybe you want to ask like how much copper or how much coal is required for the system, and so you can say, okay, in terms of brown coal and hard coal, well, this is how much you need to, that's required by the entire life cycle of the system. So then if we go to impacts, it's only showing the total. This is good information. Obviously you want to present the total impact when reporting your results, but that's about all it's giving. Now I didn't touch on this is telling you a little bit about the quality of the results. So this is to do with the pedigree scoring matrix, which you learned in the uncertainty section. So it's telling you like where there's the data is relatively good quality, or versus bad quality. So the lower the number, the better. Yeah, learn more from the uncertainty lectures and related material. Okay, process flow contributions. So this is a big sparse matrix, and we see that the dimensions are flows, elementary flows by processes. And so we were, yeah, I taught you this a little bit earlier in class with the basic mathematics. And so it's process flow contributions. And there's no similar output in the tool actually, and it's basically giving you the result from this equation. So you're diagonalizing x and multiplying it by s. So we can see, for example, here's our main process. We can say, okay, what is it, what emissions are occurring there in the system. So we have a few here. There's some heavy metal emissions. Here's some nitrogen oxides. So we can pinpoint exactly how much is contributing. So I would say this is a little bit too disaggregated of information, but again, if you have a very specific question about the total direct emissions from a particular process in your system, now this is not necessarily like direct. It's going to tell you the total, like, well, this is okay. It's direct, but it could be due to multiple reasons for that process. So it doesn't really tell you. It doesn't really answer the question why. Necessarily, depending on what the activity is. Maybe the activity is used for several things, very, very different things in your system. So this is just telling you the total. And then in a similar light, this is also telling you how much each process is directly contributing to every impact category. And we learn that equation as well. It's just it's dpro, it's cs diagonalize x. So it's just the same equation, but you add on the characterization matrix. Okay, then if we go to flow impact contributions, that we also learned that equation. It's telling you how each elementary flow is contributing to each impact category. So we see it here. D-stressor equals C, and instead of diagonalizing X, you diagonalize E, or the total elementary flows, which is S times X. All right, so that's about it for the quick analysis. There's no more tabs. And then if we go to the detailed analysis, we have some more tabs, but there's repetition in terms of what it presents. So both calculations present the same thing up to here, but now you have a new one here, which is called process upstream flows. Okay, so I already explained it a little bit in the tab, but what it is it's showing the flows by the processes, and again, it's showing what each process is responsible for. So in other words, it's showing the direct and upstream emissions, elementary flows due to this process in the system. And again, it's this calculation that's being undertaken here. S times L times diagonalize X, which in other words, if you break it down, it's S times I minus A to the power of negative 1 times diagonalize L times I to the negative 1, I minus A to the negative 1 multiplied by Y. So essentially you're taking your total output and you're just like using it as your final demand, just to relate it to the total impact responsible for every single process in your system. And likewise, a similar thing is done for upstream impacts. So just adding the C matrix, characterization matrix, and then we'll get it in terms of the processes and what they're responsible for. So for example, like if we look at the total impact due to, say, global warming, which is okay, this is a, I output this for recipe. It wasn't Tracy, so that's why these values don't necessarily agree with what you saw in the openLCA results. You see it's slightly different or updated characterization factors. That's why it's not agreeing perfectly. But nevertheless, you see that this is the total impact due to a kilogram of steel is 2.0298. So it's 2.03 kilogram CO2 equivalents per kilogram of steel produced. So if we go back to the process upstream impacts, and let's just highlight that row, we can see that the total is 8.6, right? So that number, what you might ask, why is that number not the total that we saw? Because again, this is showing what every single process in the system is responsible for. So all the direct impacts plus the impact upstream of that as required by that particular process of focus. So we see like immediately, like this is the same number as a total because this is the last process in the system that's pulling for a final demand. So this is it's 100% responsible for all impacts in the system. Whereas if let's just highlight this and go control find my pro to find another process that we created. So we have iron mine, and now we can see that it's responsible for a lot less because it's like it's just the mining part of the value chain, and we saw earlier that it was contributing not very much. Iron ore beneficiation, 65%. We see that it's responsible for more. So this includes basically the direct impact plus the mining plus whatever other inputs from a life cycle perspective. If we go to our next MyPro, which is pig iron production, we see it's direct plus everything upstream of it is contributing 1.54, right? And so if you were to look at, if you wanted to ask the question, what is the pig iron, all the impact from pig iron above, what is it responsible, or you get 1.54, and that number the number is going to be a little bit different due to the different impact methodologies, but you're gonna, because I was recipe, this is Tracy, but that number should be generally in agreement with this 75.74% of the impact, because this is telling you direct plus everything upstream of this particular activity. Okay, so I think that's it. Yeah, contribution tree. Yeah, that shouldn't be here for this part because that's not an output from Excel. That was for just for the tool. Okay, so hopefully that gives you a fairly good overview of what the results represent. And another video will be made that'll focus a little bit more on like what you can show in the context of an EPD report in the next part. Okay, great. So over and out.